What specific problem does long context tuning, LCT, aim to solve in the realm of video generation, and why is this problem significant?
Long context tuning, LCT, aims to address the challenge of generating coherent scene-level videos that maintain both visual and temporal consistency across multiple shots. This problem is significant because current video generation models primarily focus on single-shot synthesis, which fails to capture the complex narrative structures found in real-world videos, such as movies and television shows. By expanding the context window to model cross-shot relationships, LCT enhances the ability to generate sequences that reflect coherent events over time, ensuring that visual elements like character identity and background remain consistent throughout the scene. The significance of this advancement lies in its potential to bridge the gap between single-shot video generation capabilities and the authentic demands of video content production, ultimately enabling more realistic and engaging narrative videos. Additionally, LCT's ability to support autoregressive shot extension and interactive generation further emphasizes its importance in facilitating creative workflows in video production.
How does the proposed method, long context tuning, LCT, work? Please illustrate the process step by step, detailing any novel design elements introduced.
Long context tuning, LCT, enhances scene-level video generation by adapting a pre-trained single-shot video model to learn longer context windows for cross-shot consistency. The process begins with the implementation of a full attention mechanism that integrates all shots within a scene, allowing the model to capture relationships across shots. A novel interleaved 3D rotary positional embedding rope is introduced to maintain the relative positional relationships among text-video tokens while assigning unique absolute positions to each shot. Additionally, LCT unifies visual condition inputs and diffusion samples by applying independent diffusion time steps to each shot, enabling dynamic dependencies and effective cross-shot conditioning. Finally, the model employs bidirectional attention, which can be fine-tuned to context-causal attention for efficient autoregressive generation, significantly reducing computational overhead while maintaining visual and semantic consistency across generated scenes.
Can you provide a simple yet illustrative example that demonstrates the inner workings of LCT, including the specific steps and how they contribute to coherent video generation?
An illustrative example of long context tuning, LCT, in action can be seen in the generation of a scene where a character, say a woman, walks through a park and interacts with various elements. First, LCT utilizes a two-tier prompt structure where a global prompt describes the character and environment, while per-shot prompts detail specific actions, such as Character 1, woman walking, and Character 1 interacts with a tree. The model then employs an interleaved 3D rotary positional embedding to maintain the relative positions of video tokens across multiple shots, ensuring that the character's identity and actions are consistently represented. During training, LCT assigns independent diffusion time steps to each shot, allowing the model to leverage cleaner shots as visual conditions for noisier ones, thus enhancing cross-shot coherence. Finally, the model can generate the scene auto-regressively, where each shot builds upon the previous ones, ensuring that the character's movements and interactions flow smoothly throughout the video, resulting in a coherent narrative.
What are the theoretical or practical benefits of using LCT compared to existing methods in scene-level video generation?
The long context tuning, LCT method offers significant theoretical and practical benefits over existing scene-level video generation methods. Firstly, LCT enhances cross-shot consistency by employing a full attention mechanism that models all shots within a scene simultaneously, unlike appearance-conditioned and keyframe-based approaches that struggle with maintaining coherence across shots. Secondly, LCT's interleaved 3D rotary positional embedding allows the model to distinguish between shots while preserving relative positional relationships, which is crucial for coherent narrative flow. Additionally, the asynchronous time step strategy unifies conditioning inputs and diffusion samples, enabling dynamic dependencies between shots and improving the model's ability to leverage visual information effectively. Finally, LCT supports autoregressive shot extension and interactive generation, allowing for seamless content modification and narrative continuity, which existing methods fail to achieve due to their reliance on independent shot synthesis. Overall, LCT not only maintains but enhances the model's capabilities, leading to superior visual and semantic consistency in generated scenes.
How was the long context tuning (LCT) method validated in the paper? Discuss the datasets, benchmarks, and metrics used to test its performance.
The long context tuning (LCT) method was validated through extensive training and evaluation on scene-level video data collected from various public sources, resulting in approximately 1.5 million scene samples. The performance of LCT was compared against existing methods in two major categories: appearance-conditioned approaches, exemplified by Video Studio, and keyframe-based methods, including Flux Storyboard, In Context LoRa, IC LoRa, and Story Diffusion. The evaluation utilized both qualitative and quantitative metrics, focusing on visual quality, temporal consistency, and semantic coherence, with user studies prioritizing cross-shot consistency. Automatic assessments were conducted using VBench, which measures shot-level quality, revealing that while LCT performed slightly below visually conditioned baselines in visual quality, it significantly outperformed them in maintaining scene-level coherence. Additionally, ablation studies confirmed that LCT not only preserved but enhanced the pre-trained, single-shot generation capabilities of the model.
What notable results were achieved with LCT, and how do these results compare with previous methods in terms of visual quality, temporal consistency, and semantic coherence?
The long context tuning (LCT) model achieved significant advancements in scene-level video generation, demonstrating superior performance in generating visually and semantically consistent scenes, as evidenced by a generated video with around 20 shots lasting 3 minutes. Compared to previous methods, LCT exhibited enhanced semantic alignment, maintaining character identity and environmental consistency throughout the scene, which was a challenge for baseline approaches like Video Studio and keyframe-based methods. While LCT's visual quality was slightly below that of visually conditioned baselines, it outperformed them in terms of temporal consistency and semantic coherence, effectively addressing issues such as character reappearance and positional shifts that plagued earlier models. The model's ability to generate diverse framing and maintain narrative continuity further distinguished it from existing solutions, which often struggled with prompt alignment and frame composition diversity. Overall, LCT not only preserved but potentially enhanced the single-shot generation capabilities of the pre-trained model, showcasing its effectiveness in scene-level coherence.